Hey guys, welcome back to another video. In this video, we're going to look at how simple harmonic motion applies to springs. Right. So for this example, we have a pretty interesting diagram. So it's basically made with bob and spring. In this case, we're going to be using different position, be it 2, 3, and 4, to form a graph and then take a certain point and find out the forces acting on the bob, and from it get back to our simple harmonic motion formula. How do we do that? Let's go step by step and look at the initial position, which is, in this case, the initial position is basically the length of the string, right? The initial position of the not string, the spring, right? This is your length of spring, right? This is its equilibrium position without the bob. Now, the moment you add a bob, it's going to extend, and there is a displacement. What is this displacement? I am naming this displacement from this equilibrium to this new equilibrium with the bob. I'm going to name this distance x0. So we're naming the distance as x0, right? Great. So I'm naming this distance or displacement as x0. Now, if I pull this bob down from its equilibrium position, this distance, let's call it x1. Let's call this displacement x1 from equilibrium position to my pulled down position. From equilibrium to pulled down. Let's call it what? x1. Right. So the moment from this position it is released, it's going to travel beyond the equilibrium. This is the equilibrium, and it's going to travel beyond and go to a new position above, which is going to be the same distance as x1. So you can call this distance from the furthest up position to the equilibrium as x1 as well, right? Okay, so this is our distance. All of these, x0, x1, and again x1 is our distance. Now we want to plot it's actually force, right? So now we want to plot our force against time. We want to plot our force against time. How do we do that? So starting from initial position, where this is our initial position. This is, I basically added this part just for the clarity of understanding of this x0 distance. By the way, F is equals to kx0. This is your formula for springs, where k is the constant, and x0 is the displacement from EQ or equilibrium, right? So the product of these two is going to give you force. Great. So force is equals to kx0 for this position, where the force upwards is going to be given by the pulling force of the spring, which is the product of the spring constant and the displacement. This is your pulling force on the bob. And what is the downwards force? It's mg. This is your initial position, even though labeled 2, just because of this, we're going to be considering your initial position on the graph. Okay, so at this position, is there any net force? This bob is resting down from the ceiling at the fixed point after being displaced x naught due to the weight of the bob, right? So it has displaced x naught due to the weight of the bob. After it has displaced and it stops oscillating, it is going to be in its equilibrium. It reaches equilibrium because you're not pulling it, you're not pushing it, you just left the bob. And now after extending by x naught, it is at rest at a new equilibrium position, where the distance from the initial position is again x naught. Great. If you understand that, what is the upwards force on the bob due to the spring? It is kx, kx naught. This distance times the spring constant of the spring. This is your upwards force. What is the downwards force on the bob? mg. It's weight. It's weight. Great. So if you know that, you can say upwards force is kx naught, downwards force is mg. What is the force? What is the breakdown of forces in position 3 or position 2 according to this graph? So you have artificially or externally pulled the bob down from this equilibrium position downwards by x1. So if you pull it down by x1, what are the forces acting? Downwards is going to be mg. After considering you've already left it and you're not still holding the bob, you have extended the spring, you have pulled the bob and you've left it. At that instantaneous position where you've left it, the distance is x1, and the upwards force is kx naught, which was the initial force due to this extension, plus the new extension x1 times spring constant. This is going to give you the total upwards force. So what are we doing? Adding the first force, force caused by the initial extension x naught. Then we are adding the second force, again due to the spring, but due to the extra extension x1. So we are adding both the forces caused by x naught and x1. We're adding it up to get the total upwards force. What is the downward force? mg. Because at that instantaneous time where you have left the bob instantaneously, there is mg downwards and kx naught plus kx1 upwards. At this position, it's going to have maximum acceleration upwards. It's going to have maximum acceleration upwards because there is a net force upwards, because the moment you release the bob, it's going to have a tendency to move up, right? So at this position, it's going to have kx naught plus kx1 upwards and mg downwards. Again, the moment it reaches equilibrium, let's say over here it reaches equilibrium, at this position, the displacement from this equilibrium is only x naught. So it's going to have an upward force of kx naught and downward force of mg. So over here, the net force is 0. Right. Again, for this point, which is above the initial equilibrium, which is over here. Here, the displacement is, let's say, x2. We're calling it x2, right? So what is x2? It's the displacement of the spring that was initially at rest, like this. From this position to the new position where the spring has actually contracted. The distance of the spring, the length of the spring has reduced due to this oscillation, of the bob. Since you have pulled down the bob, now this bob will move upwards and cause the spring to contract. So compared to this position, calling it L1, the length of the spring has reduced and become L2, right? So since the spring has contracted from its initial length, it's going to push down on the bob. It's going to push down on the bob and cause a force kx2. What is the spring constant? K. What is the extension? Or in this case, the contraction is x2. The length of the spring has reduced. So in this case, the distance or the reduction in length is x2. So your force is actually kx2, which is acting downwards on the bob. What is the other downwards force? It is mg. So there are two forces. One is kx2, the other is mg, which is both acting downwards. So in this case, you have at position 3, let's say, you have two other forces, kx2 and mg, both of which are acting downwards. So the other thing is this kx0 plus kx1 is actually equals to kx2 plus mg. Yeah. Anyways. Oh, no. I mean the net force, which is kx1 is equals to kx2 plus mg. Since over here the net force is kx2 plus mg, over here the net force is actually kx1. Since kx0 and mg is equal, you can forget about kx0 and mg because both of these are equal. Over here the resultant force is actually kx1, and over here the resultant force is kx2 plus mg. So both of these are equal since the resultant force actually stays constant. Anyways, you don't need to know that. That is not the point of this explanation. The point of this explanation is, let's take a specific point on this curve. Let's take a specific position of the ball. Let's see for this instance where the mg is going to be acting downwards and you have two upward forces. One is kx0, the other is kx1. Okay, so if we consider these two positions, this instance where there is a resultant force, we can somehow get back to that initial proportionality of acceleration is proportional to omega squared x, right? That is the basically main point of doing this derivation for springs. We want to get back to that proportionality and prove that simple harmonic motion applies in this case as well. Okay, so we're taking this position where the net force is actually kx1. We know net force is given by mass into acceleration. We know net force is given by mass into acceleration. Therefore, we can say kx0 is equals to mg. Kx0 is equals to mg. Great. So if you know that, we can form an equation where kx0 plus kx1 minus mg is ma. Since both of these are actually equal, kx0 and mg is equal, you can cancel both of these out due to this, and you're going to be left with kx1 is equals to ma. Since both of these are equal, you can write kx0 as mg and cancel these out, and you're going to be left with kx1, which is equals to mass into acceleration. Great. Now the thing over here is you're already close to the proportionality, because see, you've already introduced acceleration into the equation. So now the other job is to prove the proportionality of acceleration and displacement. You already have the displacement, which is x1. You can name it as x or keep it as x1, both of which mean displacement. And basically in this case, in this step, you have to introduce a minus sign. Why? Because notice that if in this case we take this as positive, upwards as positive, and downwards as negative, since the net force is acting upwards, the acceleration is positive. But since the displacement of the bob is downwards of equilibrium, the displacement x is going to be negative. So you have to add a negative sign in front of the displacement. So let's do that. We are going to introduce this negative sign due to the opposite direction. You can do it over here as well. It means the same thing. So now make acceleration the subject, and you have yourself the same proportionality as before. The same proportionality as before. Acceleration is proportional to the displacement, but in opposite direction. Right. So from this, again, you can do the same thing as before in the previous video for what was it? For pendulum, right? So for pendulum, you equated the constants. In this case as well, so you can do the same thing, because both omega square and k by m, these are going to be equal. The constants are going to be equal. You can again test this yourself. If you know the spring constant, know the spring you're working with, and if you know the mass of the bob, you can find out the constant k by m. And after doing the experiment, if you find out the time period, you will be able to figure out the omega square as well. So you're going to see that the omega square and k by m is actually equal. So you can do this, do the experiment yourself and prove this. But anyways, in this case, let's derive the formula. So basically, omega square is equals to k by m, as explained. And if you input the expression for omega, it's going to be 2 pi by t whole square is equals to k by m. Right. So from this, if you make time period the subject, you take a square root over k by m, and basically if I break it down, two pi whole square by time period square is k by m. Make time period the subject. So in this case, you're going to be left with time period is equals to m by k times 2 pi whole square. Let's take this above and basically introduce a square root. So you're going to be left with 2 pi. Why? Because the square root of 2 pi whole square is 2 pi. Right. So m by k, root over m by k. This is your expression for time period. This. So basically, we're getting an expression for time period in case of the spring experiment. Right. So if you know the mass, if you know the spring constant, you can find out the time period. Notice an interesting thing to notice over here is the time period is actually the same no matter how far you displace the bob. You can test it out yourself. Basically, the frequency of the bob doesn't change. The frequency of the spring doesn't change. Basically, there is a resonant frequency of the object. We're going to talk about resonance and damping in the next few videos. So I'm just giving you a little pointer. Basically, no matter how far you displace a spring or how far you displace, okay, not for the pendulum, but up till 15 degrees, doesn't matter how if you displace it by 2 degree, 5 degree, 10 degree or 15 degree, you're going to see that the time period doesn't change. The time period actually remains same. So from this, you understand that there is a certain frequency at which every object works. So let's take the spring for example. If you pull down the spring by, let's say, at first by 5 centimeters, you're going to see that it completes, let's say, the same number of oscillations, say 5 oscillations under 10 seconds. If you displace the spring, by, let's say, 5 cm, you're going to see that, for example, it completes 5 oscillation within 5 seconds, or let's say 10 seconds. Within 10 seconds, it's completing 5 oscillation after displacing it by 5 centimeters. If you displace the same spring by 10 centimeter, it's still going to give you 5 oscillations under 10 seconds or with 10 seconds. For after 10 seconds, you're going to have 5 oscillations, right? So even if you increase this and take this up to 20 centimeters, even in this case, you're going to get 5 oscillations by 10 seconds. So the frequency or the time period does not change depending on the length by which you displace the bob from its equilibrium. Therefore, there is a certain frequency at which every object works or prefers to oscillate in, and that is not affected by its length or its displacement. It's only going to be affected by the object itself, which is its spring constant, its tendency to contract or extend. That is its spring constant. The other variable is the mass. The mass it's trying to pull up and pull down, right? So these are the only two variables that can meddle with your time period or frequency. Great. So now we understand how we can find out the time period. The only thing you need, mass and the spring constant. So how did we do this? In summary, from before, let's see. The first thing we did is we took one example, an ideal example where you have a resultant force, So over here, you have the resultant force of kx1, because kx naught is equals to mg, right? Kx naught is equals to mg. Why? Because in this position where the bob is in equilibrium, kx naught, the force caused by the spring, is acting upwards and is equal to the mg since it is in equilibrium, right? So we're not taking that example, but we're using this equation of kx naught is equals to mg to help us with this equation, where we're cancelling out kx naught and mg from the equation. How? Since they are in the opposite direction and equal, we can cancel them out. And we're left with a nice equation of kx1 is equals to ma. If we know that, we know displacement is actually in the opposite direction compared to acceleration. So we introduce a minus sign. After we do that, make acceleration the subject, and you're going to get your proportionality of acceleration is indeed proportional to the displacement and in the opposite direction. That is how we prove simple harmonic motion in the pendulums. In the case of springs. So again, you can do this experiment yourself and try it out. And let me know. Right, so see you in the next video.